You ever wonder why some rooms just feel right while others are just impossible to be in? Well, today we're going to pull back the curtain on the invisible architecture that's all around us, the science of sound. You know that feeling, right? Where you just feel completely overwhelmed, you can't focus, you can't relax, all because of the sound of the room you're in. It happens all the time. Think about the classic open office. Yeah. Every single conversation, every little keyboard click, it feels like it's happening right inside your head. It makes it almost impossible to get anything done. Or how about that trendy new restaurant? The food's amazing, but the place is just a wall of noise. Clattering plates, 100 conversations at once, and you end up having to literally shout at the person sitting right across the table from you. And then you've got those huge cavernous lobbies. You know the ones, where every single footstep just echoes and echoes, making the whole place feel kind of cold and, well, empty. These aren't just little annoyances. They're actually failures of design. And to really get why, we need to start with the basics. So, before we can talk about fixing these spaces, we have to get a handle on what we're dealing with. So, what is sound really? Okay, so at its most basic, sound is just a vibration. That's it. It's a physical wave of pressure moving through the air. And for sound to even happen, you need three things: a source, to make the vibration, a path for it to travel on, and a receiver, like your ear, to actually pick it up. Now, every single sound wave has two key ingredients. First up is frequency. That's just how fast the wave is vibrating. Our brain hears that as pitch. So really fast vibrations give you a high-pitched sound, and slow vibrations give you a low, rumbly sound. Then you've got amplitude. That's the wave's raw power, which of course we hear as loudness. And here is where things get kind of mind-bending: the actual physical size of these waves. High-pitched sounds, like a little whistle, create these tiny little waves, smaller than an inch long. But a low-pitched bass note from a big speaker, whoa, that can create a physical wave that is over 50 feet long. I mean, just try to picture a wave longer than a school bus moving through your living room. So you've got these, in some cases, massive waves moving through space. But how does that physical pressure turn into something we actually hear? Well, that's where the receiver in our little equation comes in, the absolutely incredible human ear. It all happens in three main steps. First, the outside of your ear, the part you can see, acts like a funnel, gathering up those sound waves. Then, the middle ear takes over, and using these tiny little bones, it amplifies that vibration by up to 25 times. And finally, the inner ear, specifically this cool snail-shaped thing called the cochlea, converts those super-powered vibrations into electrical signals that your brain can finally understand as sound. Okay, so measuring loudness is, well, it's kind of tricky. Our ears can handle a ridiculous range of power, so a simple scale from like 1 to 10 just wouldn't work. So instead, we use the decibel scale. A good way to think of it is like the Richter scale for earthquakes. It's designed to manage huge differences in power in a way that actually matches how we perceive loudness. The scale starts at 0 decibels. That's about the quietest sound a human can possibly hear, and it goes all the way up to around 130. And that's the threshold of pain. That's the point where sound is so intense, it actually starts to hurt. So let's put that into perspective, right? The rustle of leaves in the wind, that's about 15 decibels. A nice quiet room is double that, around 30. You and me talking like this, that's about 70. But a jet engine passing close by, that can roar past 140 decibels, pushing way deep into that painful range. And here is where the math gets really, really weird. Because the scale isn't a straight line, you can't just add the numbers up. So if you have one speaker playing at 60 decibels, and then you add a second identical speaker, you don't get 120 decibels. You get 63. I mean, you literally doubled the sound power, and the level only went up by 3. It's wild, right? But for all this complexity, our brains are just incredible processors. Think about what's known as the cocktail party effect. That's your brain's amazing built-in ability to just lock onto one person's voice in a super noisy room and filter out pretty much everything else. It's a superpower we all have. So, our brains are great at filtering sound, but what happens when the room itself starts working against us? This is where we put the wave and the receiver, our ears, together inside a building. And this is where physics meets architecture, and we get the good, the bad, and the echoey. Let's talk about reflections. Now, they're not all bad. The good kind of reflection creates reverberation, or reverb. Reverb is our friend. It gives music a sense of warmth and makes the speaker's voice sound full and rich. But when a reflection is too loud and too delayed, it becomes an echo. An echo is our foe. It makes speech hard to understand and music sound all muddy. The actual shape of a surface makes a huge difference too. And here we have another hero and a villain. Our hero is diffusion. This happens when sound hits a surface that curves outward. The waves scatter evenly all around the room, and it creates this really pleasant, balanced sound. But the villain is focusing. That's when sound hits a surface that curves inward, like a dome. It acts like a magnifying glass for sound, creating these intense loud spots and other areas where you can barely hear anything at all. You ever clap your hands in an empty hallway and hear that weird, zinging, ringing sound? That's a real thing. It's called flutter. It's what happens when sound gets trapped between two flat, parallel walls, bouncing back and forth so fast that it just turns into this buzzing, clicking echo. Okay, so with all these potential problems out there, echoes, focusing, flutter, how do designers and architects actually fix them? How do they build spaces that sound as good as they look? Well, the biggest secret is in the materials they choose. The number one tool in the toolbox for fixing bad acoustics is sound absorption. And the goal is pretty simple. Instead of letting sound waves bounce all over the place, you use materials that stop them in their tracks. It works by taking that sound energy and converting it into a tiny, tiny amount of heat, which basically just kills the reflection. And this is where the choice of material becomes absolutely everything. So a hard surface, like drywall, it reflects pretty much all the sound that hits it. A thick, heavy carpet does a much better job of absorbing it. But the real champions are the specially engineered acoustical tiles. They're literally designed to just soak up a huge percentage of the sound energy in a room. So I think the main thing to take away from all this is that sound isn't just some afterthought. A poorly designed acoustic environment really does get in the way of a space's function and our ability to enjoy it. It's not just about noise. It's about our mood, our ability to get things done, and even our well-being. So, I'm going to leave you with a little challenge. The next time you walk into any room, your office, a restaurant, even your own home, just stop for a second, maybe close your eyes, and just listen. What is the invisible architecture of that space trying to tell you?